Thank you so much. So our next speaker is Richard from Accelsius, please.
Thanks, Lesia. All right, great. Yeah, so hi, I'm Dr. Rich Bonner, CTO of Excelsius. We are a direct-to-chip, two-phase company located in Austin, Texas. Started over 2 years ago, and we're happy the OCP is having us here to present on our technology and some of the sustainability impacts associated with it. So first, I just want to make the point that your cooling solution underpins any energy or water conservation efforts that you're trying to achieve. Having a thermal solution with lower thermal resistance ultimately is what's going to lower energy consumption, lower water consumption. It's also going to enable heat reuse and all the other things we're trying to do in regards to sustainability. I'm going to share the results of our two-phase cooling technology because we're excited by the performance that we're seeing and the impacts we think that's going to have on sustainability. Of course, with two-phase cooling, if you're familiar, we're using refrigerants that are considered PFAS. So we are also going to cover the PFAS issue, give a kind of a broad overview of it, why it's earned the moniker of a forever chemical, but we're also going to share why the refrigerants we're using shouldn't be and really aren't being classified as forever chemicals, and even give some chemistry-based fundamentals as to why that is. So first, some of you might not be aware of two-phase cooling, so I just want to give an overview of the mechanism. Basically, with two-phase cooling, you're bringing a liquid near its saturation point over your heated component. As it gets near that and heats up, you create vapor. What's great about this is in order to increase heat transfer, you want to disturb the boundary layer. Since we're creating vapor right at that interface where that boundary layer exists, you're inherently getting almost ideal mixing. The other benefit of two-phase cooling is that when you remove the heat, you're using the latent heat of vaporization. So ultimately, we don't need as much fluid to remove the same quantity of heat as you do with a sensible based technology such as single-phase water, single-phase dielectric, or single-phase immersion. We've written a paper, if you want to learn more about this, we did write a nice paper with Professor Mudavar from Purdue. He's renowned in two-phase cooling, can be found in Data Center Frontiers, but it gives a lot of general background on two-phase cooling if you want to educate yourself some more. Next, I'm going to just talk about general pros and cons of two-phase cooling, some of which I alluded to in the previous slide. First, again, because of that boiling mechanism, we tend to get thermal resistances that are the same, if not even lower, than single-phase water. We don't rely on forcing flow through small channels, right? We're relying on that boiling mechanism. So even some of the filtering requirements and other things are going to be less important with two-phase cooling. And we don't have to worry about erosion because, again, we're using less flow rate due to that latent heat effect. We're using dielectric fluids, so even though in our solution we don't expect fluid to leak, if it does, similar to the other forms of immersion cooling, it's not going to short out your electronics. Another one that we're finding, another advantage of two-phase cooling is thermal uniformity across the chip. Anytime you're doing a single-phase mode of heat transfer, ultimately your fluid is heating up as it travels across the chip, which is going to cause you to have certain hot spots. This problem is becoming amplified if you're following some of the GPU architectures. They're putting memory modules close to logical processing modules. The memory modules themselves typically have, even though they're lower flux, a lower temperature requirement. So where typically thermal designers want to bring their coldest fluid to the hottest portion of a chip, they're challenged that if they do that, now that fluid is too warm to enable cooling of those lower flux components that have lower temperatures. In a two-phase cooling-based approach, we always boil at the saturation temperature. So no matter what type of module, you're ultimately sinking your heat to a same temperature. One of the challenges is, though, when you're doing two-phase cooling is that you're not using air or water as a coolant, and if you're not, now you have to worry about all the things that come with that: toxicity, flammability, and environmental concerns. And we have fluids that are going to check those boxes, but it's a concern because, again, we're not using air or water. And if you don't have an expertly designed solution, there's a risk of dry out. If for some reason you don't have enough liquid at that chip to boil, not only is your performance degrades, not only to poorer forms of heat transfer, actually it's one of the worst. It's almost like we approach air cooling, which is not good. But Yeah. Next, I just want to do some specifics on two-phase cooling pros and cons. First, addressing direct-to-chip. So with direct-to-chip, one of the pros is that we are going to have much lower mass flow rates. I talked about that latent heat versus sensible heat. When you run the numbers to remove the same amount of heat, ultimately you will need 4.5 to 9 times less mass flow rate with two-phase cooling compared to single-phase water, and all the benefits you can imagine that come with that. We're using a familiar rack architecture, similar to air, similar to single-phase water. And also there's even some use cases, maybe not 100 kilowatt racks, maybe more like 20 kilowatt racks, but it is possible with these two-phase cooling mechanisms to passively circulate fluid. In other words, use the density difference to drive the fluid through, which could offer you some reliability benefits over a pump-based solution. For immersion, with two-phase cooling compared to single-phase, you probably don't need an in-tank fluid mover. It can be passive, and you are going to get more fluid circulation in two-phase immersion than you would in single-phase immersion. Challenges, of course, may be that vapor leaks out during routine maintenance. I think we've also seen that these coolants for immersion cooling are more specific for two-phase. So right now, they're more expensive compared to the refrigerants we can use with direct-to-chip two-phase, which are basically leveraging the scale that already exists for HVAC and other vapor compression applications. So next I want to use our Excelsius newcool platform to just demonstrate what a direct-to-chip two-phase cooling system looks like. If you look at the picture there on the right, this should look very familiar to anyone who's familiar with single-phase water cooling. You'll see a CDU, same redundancy and reliability as a single-phase water CDU, sort of anchoring the bottom of the system. We have a manifold with quick disconnects for providing liquid to the servers. We also have a manifold, now it's a vapor manifold, to collect the vapor that comes off the chip, ultimately bring it back to the CDU. One difference, the only difference I think that you would notice from the outside is we have a reservoir that's located at the top of the rack. The reservoir serves the purpose of allowing for that expansion of liquid and vapor during phase change, and ultimately that allows us to prevent cavitation and other things during startup and rapid changes in power load. I'm going to play a video while I go through the rest of this. This is just showing some of the boiling process in one of our newcool evaporators. Finally, I'm going to introduce the figure on the left on this slide. This is just an implementation of our solution into a 2-processor server. This is basically we're using our solution to cool 2 Xenon 4th generation Sapphire Rapid chips. And I'm going to now show some performance testing that we've done on the next slide of that system we're showing there. Okay, so what we did here is we have a full rack, fully populated rack that we're running at a 50 kilowatt total power load. And we test actual Intel chips. These aren't test vehicles. This is actual measured junction temperatures on Intel chips for that 2-processor server that I was showing before. And we run it at 3 different facility water temperatures. So just for clarity, I'm not showing the temperature of the fluid entering the server. This is actually the temperature of the facility water that will be entering the CDU, again, of this rack that's running at a 50 kilowatt power load. On this plot, we're showing junction temperature versus CPU power. The top 2 lines, the top one is basically the max temperature before your Intel chip would just turn off. The green line is the temperature at which you would start to throttle. That's at about 80 degrees Celsius. You can see that even with 45 degrees C facility water coming to the back of our rack, of a fully loaded rack, the max temperature we saw at full power on these CPUs was roughly 73 degrees C, well below, about 70 degrees below the throttle point. So this opens up a lot of possibilities, right? No throttling, you can maybe even overclock if you want to. If you want to run with cooler facility water, you might get longer life out of your chips. And maybe most excitingly is the possibility for heat recovery. 45 degrees Celsius is not only enough to heat pools and homes, but even hot water for the home. So, all right, next most people are interested in AI chips and NVIDIA-based chips. So here we've done some testing on a thermal test vehicle where we've sized our thermal test vehicle to match the logical portion of the GPU, sort of putting all the heat there rather than spreading it out to any of the memory modules. We test at a 40 degrees C temperature going into the cold plate itself. And here you can see we're able to test successfully from 200 watts up to 1,000 watts on that thermal test vehicle. For a point of reference, the current H100 runs at roughly 700 watts. You can see we point that out there. So at a 40-degree C inlet to the cold plate, our case temperature was roughly 57 degrees C, and that was well below the throttle point, which is expected to be around 69 degrees in terms of case temperature. The junction temperature is closer to 87 degrees C. As a point of reference, we put in some information for a single-phase water cold plate tested over a range of flow rates at 700 watts. That's kind of what you see in that error bar. And what we're showing there is the change in performance from 1.5 liters per minute of flow down to 2.5 liters per minute of flow. You can see in their case, it ran a couple degrees hotter, maybe much closer to the junction temperature. Also, what I like to show is the difference in performance as you compare it based on heat flux. So if you look at the sort of x-axis that's located on the top, you'll see that the difference in heat flux we're able to achieve before hitting the case temperature is roughly 30 or 40% more than the similar power density or heat flux that we're able to see with single-phase water at an equivalent operating condition. People want to talk about the future, so for fun, we started ramping up our power even more on the same thermal test vehicle and also increasing the flow rate to see what happens. We were able to get to 2,200 watts on, again, this H100 sized thermal test vehicle, 3 times the power of current GPUs without dry out. People have been asking lately, well, what does this mean in terms of B100 now that NVIDIA has announced that a few weeks ago? The B100 is basically going to have around 1,200 watts of power, but its heat flux is going to be similar to that of the H100. So we're expecting the case temperatures to be similar. We haven't built a TTV for the B100 yet. We're rushing to do that. But I think the fact that we're able to do almost double the power of a B100 on a smaller, more dense thermal test vehicle certainly shows the promise of our technology and our expectation that we're going to be able to cool that GPU as well. So now I'm going to switch gears and talk about sustainability, energy and water, and the promised covering of the PFAS topic. So data center water and energy use, right now, the best research I'm seeing is showing 1 to 1.5% of electricity on Earth. It's hard to pin down the PUE for that average over the entire world, but talking with analysts and trying to add that all up in my head, I get between 0.3 and 0.5% of electricity on Earth being used for data center cooling, fairly significant. Data centers are also among the top 10 water-consuming industrial commercial industries in the US. My favorite quote or thing I've seen in a paper, some researchers have looked into water consumption at the data center level, even at the power plant level, because power plants use a lot of water, and they show that a typical 20 to 50 question answer session with ChatGPT uses about half a liter of water. I want to make the case that water usage really, to be done right, needs to be thought of holistically. Power plants use a lot of water. So anything that's addressing energy efficiency is ultimately addressing water usage because you're using less energy, you're saving water at the power plant. From an energy standpoint, I worked on a calculator, the version 4 of the Green Grid total cost of ownership model. That model predicted about 49% energy savings with direct-to-chip two-phase cooling. So what about water? Well, water it's site-specific, and it really depends on how our cooling technology is used. Certainly, I've made the case that if you want to dry cool your data center, you can, but you don't have to. So I would love to put a number there, but I just can't because of the site-specific nature of it. But I would make the case that if you're saving 49% on energy, ultimately, I think your water savings is probably on the same level. But again, it depends on the site. I'm also not going to compare energy savings for my form of cooling technology, liquid cooling technology, compared to the other forms. Honestly, if we look at all of them, whether it's immersion, single-phase water, they all do much, much better than air. And you're looking at very slight differences, regardless of which form of liquid cooling technology that you use. So PFAS, here's a specific sustainability challenge for the direct-to-chip two-phase cooling. First, I want to note that PFAS encompasses a large range of chemicals. It's no different than saying hydrocarbon. You know, if you were to try to ban methane because you wanted to ban methane, but you say, okay, we're going to ban all hydrocarbons. That's crazy, right? Because hydrocarbons includes gasoline, candle wax, plastics. It's a lot of things. PFAS is the same thing. Now, the moniker has been earned by the solid forms of PFAS, things like Teflon and others that form microparticles in plastics, find their way into waterways and organisms, and honestly, some of those particles aren't treated well by organisms. They tend to stay inside of them. So I think that the forever chemical moniker has been earned, but maybe it shouldn't have been applied to PFAS in general. It should have been applied to more specific forms of PFAS. Liquid and vapor has forms of PFAS have a much different life cycle. So moving towards that, I want to make the case that not all PFAS are forever chemicals. So I'll describe the life cycle of the PFAS that we're using in our direct-to-chip two-phase cooling system. Number one, we don't expect to have leaks, right? So we're going to treat any PFAS refrigerant fluids the same way as an HVAC system. Most HVAC systems never have a leak. When they reach end of life, you recycle it. You send that fluid to a network that's an infrastructure that's in place to take that PFAS back and recycle it. In the event of a leak, what happens is that basically these refrigerants are vapor, and they start to travel into the troposphere, which is where we all live, and within a few days, before it gets to the stratosphere where the ozone ultimately could be impacted, these new fourth generation chemicals break down, and they break down into different chemicals that are actually found in nature. I have a couple more slides. I'm going to break that out in a little bit more detail. Before I get to that, I just want to comment on the regulations that have been touching PFAS. One is that, again, the refrigerants we're using aren't involved in any of the current US EPA's list of banned substances regarding drinking water regulation. I also note that these two-phase cooling systems seem to be covered under refrigeration devices that are being given leniency regarding the EPA regulations, but it's less clear what's happening there with immersion. Okay. The R1233ZD is the fluid that we use. So I just want to give some background on the chemistry here. The reason why this fluid is more safe than others has to do with the double bond that you see there. So most refrigerants, although they break down into the same constituents that we see here with R1233ZDE, they do it much more slowly because they have a single bond. The double bond there is the key that allows us to break down more quickly. And I'm going to go a little bit fast. So the main compound that it breaks down into is called trifluoric acetic acid. You're probably wondering, well, now what's that? Sounds like just another chemical I should be scared of. The truth is TFA exists already in the oceans. It's been there at micro concentrations for over 1,000 years based on estimates. If they add up all of the TFA that's expected to be created in the next 20 years, it's only going to raise the background level by at most 7.5% compared to the baseline that's already there. TFA is essentially a salt, so your body, even if you ingest it, your body has natural ways of getting it out similar to other salts. Great article there if you want to read more on that. So to summarize, your cooling solution underpins your energy and water sustainability. Two-phase cooling offers some of the highest performance that we're seeing in terms of liquid cooling technology, and therefore reasons to believe it is the most sustainable. PFAS is certainly an issue that we're all concerned with, but I think if you look into the details, you'll understand that these refrigerants we're talking about here don't deserve that label of forever chemicals, and in fact we hope that when Calmer has prevailed, the regulation supports that. So with that, open up for any questions. Thank you.
Thank you so much. We have time for one quick question before our next speaker is preparing.
Hello. There are billions of cooling systems on the planet that are leaking every day. Okay?
Sorry.
I just said there are billions of systems on the planet that are leaking every day with refrigerants. So leaking is a common thing. They aren't just recovered at the end of their life. TFA is not natural. And there's plenty of studies that are proving that that's actually what your claim is untrue. And that now that it's spiking massively, and that is why the refrigerant that you put on that list is actually being banned in Europe. Okay, that's why it's on the list to be removed, because of the PFAS issue. Okay, so I'm just confused as to why you're spewing this information out, which is quite clearly misleading.
So I'm not a PFAS researcher. I just know what I've read in the literature. And my paper I've cited there is a reputable paper, and I think it's against what you've said. But I'm open to hearing more. If you have other literature you want to share with me, I'm open to it. But.